This conference will now be recorded.
Hello everyone, crystal field theory. So this is the topic we'll start today. Two theories we have already discussed for coordination compounds. One is Werner's theory, and after that there is valence bond theory. Today the third theory. In this theory we'll be able to overcome some of the limitations that are still present in case of valence bond theory. Okay, that is the second theory. So crystal field theory. Now it will be able to explain some of the properties like color, magnetic behavior. So these properties are basically the limitations that we have seen in case of VBT. Now what are the salient features of this theory? One by one we will see. Crystal field splitting theory, in short we will call it CFT. It is basically electrostatic model. So in case of VBT theory, what we have seen, it is based on coordinate covalent bond interaction. That is the interaction between metal and ligand. We have assumed that it is completely covalent coordinate type. But in this case, now the assumption is completely opposite. Now we will consider it as completely ionic interaction. That means electrostatic interaction. So it is based on electrostatic model which consider the metal ligand bond to be completely ionic, and it is mainly occurring because of the electrostatic interaction between the metal ion and the ligand. Just imagine the ionic, very good example of ionic molecule what we know is NaCl. Now NaCl, how the bond is formed, it is basically the electrostatic interaction between the positive charge of sodium and negative charge of chlorine. So this is electrostatic interaction between these two, and that is known as ionic bond. So in this case also it is assumed that the metal ligand bond, it is completely ionic in nature. Fine, that means there is electrostatic interaction present between the metal ion and the ligand. Now ligand can be two types. One is neutral, for example ammonia, water. So these are neutral molecules, or it may be ionic also. So all the halogens, they are basically very good example of ionic ligand, that is Cl minus, Br minus. You can also take the example of Cn minus. Now these are ionic ligands. So when it is we are considering anionic ligands, and when we are considering neutral molecules like ammonia and water, two separate things you have to see. Ligands are treated as point charges when they are anion. So for anionic ligands like this, they will be considered as point charges, and if it is neutral molecule, then you have to consider it as dipole. So for example, if you take water molecule, oxygen is more electronegative, so the direction of dipole moment, it is towards oxygen. So more negative charge is present over oxygen and positive charge over hydrogen. This is partial charge, del sign is used. So now this is considered as dipole, as the negative end on one side, which is the oxygen side, and the positive charge that is on the other side towards hydrogen. So in this way it will be considered as dipole. And next come to metal. Metal, it interacts with these ligands with their d orbitals. Okay, now there are total 5 d orbitals when they are isolated gaseous metal atom on Earth. So isolated, that means now they are not, suppose they are not interacting with the ligands, they are free in nature. Now it may be carrying any positive charge, it may be in neutral state, both are possible. So that is why it is written metal atom, that is when it is neutral, and it may be ion also if it is carrying some negative charge. Fine. So when it is in isolated state, or irrespective of there is any oxidation state present or not, now all these 5d orbitals, they will have same energy, and there is a specific term which we use for same energy, and that term is degenerate. So we can say that the 5d orbitals of metal, when they are not interacting with ligands, that is they are in isolated state, under that condition all the 5d orbitals are degenerate, that means having same energy. But when the ligands are now started interacting with the metals, now these 5d orbitals, they will no longer be having the same energy. Fine. So out of these 5, some d orbitals will be having higher energy, and rest of the d orbitals, they will be having lower energy. And why it is so? detailed explanation we will see in the upcoming slides, right? So when this there is ligands metal interaction already started, this degeneracy will be destroyed. So this degeneracy will be maintained if a spherically symmetric field of negative charge surround the metal atom. So suppose if when ligands are interacting like this, if surrounding the metal atom, whatever direction you move, suppose in all direction you are getting same type of charge, okay, that means spherically symmetric field of negative charge, whatever direction you move you will always get same amount of charge. Only though this is very ideal case, but suppose if it is the case, then degeneracy can be maintained, but actually in practical situation that doesn't happen. So what is the effect of this? The effect is now degeneracy is destroyed. So when this negative field is resulted by the ligands in a complex, now it is no longer symmetric, now it becomes asymmetric. So degeneracy will be destroyed, that is removed, and ultimately there will be splitting. So some d orbitals will be having high energy, some will be having low energy. Now this pattern of splitting, that depends on the nature of crystal field. So this splitting actually depends on so many factors. One by one we will see all these factors. But right now just try to understand when ligands are not present, and if ligands are present and there is an ideal condition that surrounding metal you have symmetrical field of negative charge, but that is not actual case. What happens actually, the field is basically asymmetric, and as a result degeneracy is destroyed. Okay, now how to know that which d orbitals will be having higher energy, which d orbitals will be having lower energy? If we want to understand that, so we should have proper knowledge about the orientation of the different d orbitals of the metal. So just forget about metal ligand, forget about crystal field theory, just focus on the d orbitals, how the 5 d orbitals of metals are actually. Okay, then only we can and if it is clear to us, then only we can understand how these d orbitals are interacting with the ligand. So in the next slide, now you can see here we have 5 d orbitals. So what are these 5 d orbitals? D, y, z, x, y, and x, z. Why I have marked these three? Because these three orbitals, there is some similarity. What is the similarity? The similarity is the lobes are in between the axes. So if you just look at these 3d orbitals that I have marked with red color, you can see all the lobes are in between the axes. So when it is yz, that is when I am saying it is dyz, that means lobes will be in between the axes of z and y. And x, it is perpendicular to z and y. When I am saying it is dxy, now in the xy plane, this d orbital will remain, but see the lobes are in between the axes. When I am saying it is dxz, now this is the plane of dxz, now y is perpendicular. So in this plane, again the lobes are in between the axes. Fine. So this is the three types. Then the fourth one, d, when I am saying it is dx square y square, now again it is in xy plane, just like this. But try to understand the difference. Now the lobes are along the axis, as if the axes are cutting through the lobes, right? And when it is dz square, it looks to some extent different, but here the lobes is again through z axis. So dz square means it is directly on the z axis. So you can find some similarity between these two, because here the lobes are directly on the axis, and you can also find the similarity for these three, 1, 2, 3. So 1, 2, 3, there is some common point. Lobes are in between the axis, and when it is 4 and 5, there is also a common point that the lobes are directly on the axis. So d orbital, how it looks, if it is clear, then only we can understand how they are interacting with the ligands negative charge. So please mention if there is any doubt regarding the d orbitals, because if d orbital pictures are not clear, you will not be able to understand how these d orbitals are interacting with the ligands. Okay. So is there any doubt? So next we will see how they are interacting with the ligand's negative charge. So first we have taken these three orbitals. Remember, it has some common point, and these three orbitals together it will be under the category T2G. Now these three we have taken together because there is some common factor. Lobes are in between the axes. Here this spherical shape, that is actually the ligand point, that is it signifies the ligand, and in the center that you are seeing, it is actually the metal. So metal is having all these d orbitals. Now when it is dxy, obviously the lobes will be in the plane of xy. So now the z axis, that will be perpendicular to the screen of the laptop, right? When it is dxz, now the lobes will be in the plane of zx. So now we have taken zx on the plane of screen, and y-axis will be perpendicular to the screen. And for dyz, now you have to take z-axis and y-axis. Lobes will be in between the axis, and now x-axis is perpendicular to the screen, because all the three axes are basically 90 degrees to each other. Okay. And as we are considering crystal field splitting in octahedral field, and in octahedral field, try to remember the geometry. Here we have a square plane and two more ligands like this. Okay. Now basically here you can consider as if this axis is z, another axis is x, another one is y. That means when the ligands are interacting, basically how the ligands are approaching in this way, and also transposition. So when the ligands are basically coming towards metal, they are coming through axis. So that is why you will see all the ligands that are denoted with this sphere shape, that are always directly on the axis, right? All these are on the axis. So here the important point to understand, the ligands when approaching, their approach as it is on the axis. So there is no direct interaction with the lobes of the metal, with the lobes of the d orbital of the metal, right? So this is common point. So ligands are not interacting directly with the lobes, because lobes are in between the axis and ligands are coming directly on the axis, right? So the lobes of T2G set of orbital, T2G set means here you have dxy, yz and xz. So the lobes of T2G set of orbital point in between x, y and z axis, but the ligands are approaching directly on it. So there is no direct interaction. So as a result, what will happen? These three orbitals, that is the T2G set, that will be lowered in energy because there is no such direct interaction. But for the other two, now the case is opposite. When it is other two, that is dx square and dz square, now what will happen? Dx square y square also, the orbitals they are on the xy plane. So see here the screen is basically, plane of the screen is xy plane. Z axis is perpendicular to the screen, that is z axis is towards us and away from us. Similarly, when it is dz square, obviously now z axis it is on the plane of the screen. X axis you can take on the plane of the screen, you can also take y axis on the plane of screen, that doesn't matter because now it is all about z axis only, xy not important. And as we know, ligands are always approaching through the axis and lobes are also on the axis. So now what will happen? There will be direct interaction. So this type of direct interaction you have not seen when it is T2G set, but in case of EG set, now there is direct interaction. That is why energy of these two orbital, it will increase. Okay, so 5d orbitals, suppose if I am writing like this, all these are having same energy, but when it is in presence of ligand, now there will be two set, that is EG set, that are higher in energy. So if you consider this is the average energy, these two orbitals under Eg, they will now have higher energy compared to the average position, and T2G set that will have lower energy compared to this average situation. This is the average. Okay, so that is why now there is splitting. Now you cannot say that all the d orbitals are generated. There are two category of d orbitals. So in this slide, is there any doubt? Should I repeat any part? So this is degenerate d orbital when it is free ion. That is, suppose if it is Mn plus, N may be any oxidation state. Now when ligands are approaching, the energy is slightly increased. But this is imaginary case. This is possible. See, here energy is increased because if this is the energy axis, compared to this situation here, energy is increased because now ligands are they are starting to interact. But still all the d orbitals are degenerate because we are now considering ideal situation, which is actually not present. So what happens actually, there is two set Eg and T2G. Under T2G you have these three orbitals, under Eg you have dz square and dx square y square. And the gap between this Eg and T2G, this gap, that is denoted by either del O, this type of sign, O means O for octahedral, or you can also write it as 10 dq. Now there are two different unit scale is there. Del O, it is actually equal to 10 dq. That means del O, this unit is larger, or you can say that 1 dq, that is actually equal to 1 by 10 of del. Both are correct. So two way we can express it, and as this T2G said they are lower in energy. So when you will consider this, that is for individual electrons, suppose there is 2 electrons. So for 2 electrons, how we will do the calculation? In terms of dq, now you will multiply -4 into 2, but in terms of dq. But if you are considering del O, because del O is larger unit, so now it will be minus 0.4 into 2 if it is in terms of del O, because it is 1/10. Okay, 1/10. So that is why it is 0.4, not 4. So in terms of dq it is 4, in terms of del O it is 0.4. Similarly, when you are considering this gap, it is +6 for dq but plus 0.6 for del O. And CFSE means crystal field stabilization energy. So in this way we can calculate crystal field stabilization energy depending on how many electrons are there. So suppose if there are 2 electrons, it will be -4 into 2, that is -8 dq. Suppose if there are 3 electrons and then 4th electrons here, so what you will do, 3 into -4, that is -12, and 6 into 1, that means -12 plus 6, it will be -6 dq. Okay, and if it is in terms of del O, it will be -0.6. So the orbitals lying along the axis, that is this Eg set, will experience strong repulsion with the negative charge of ligand, right? And there will be raise in energy to a greater extent than the orbitals with lobes directed between the axis. Now, which lobes are directed between the axis for T2G set? Thus, degeneracy is destroyed, and degenerate d orbitals, now they are splitting into two sets. One is T2G, another one is Eg, and the process is known as crystal field splitting. But remember, it is only for octahedral field. That is clearly mentioned here, because if it is tetrahedral field, the situation is completely different. That we will discuss separately. Okay, right now just try to understand it is only for octahedral, not tetrahedral. Okay. So this difference between these two sets, that is T2G set and Eg set, that is known as CFSE, or crystal field stabilization energy. Now this is represented by del O or dq, and here O stands for octahedral. Now this energy gap, it falls in the region of UV visible spectrum, because we know there are different regions depending on which wavelength or frequency the energy is matching to. Depending on that, we can have different region in the electromagnetic spectrum if you consider. Fine. So it falls in the UV visible spectrum. So that is the reason UV visible means if it is purely in UV, you will not be able to see any color for the complex. But suppose if it falls in the visible region, now there will be some color shown by the complex. Okay, so that is why some complexes are having color, though most of the complexes are having color, but sometimes it may be colorless also. Both are possible. So here one example of calculation I am trying to show. So suppose we have this EG and T2G, and now you have placed electrons. So suppose it is D4 system. So for D4 system, 1 1 1, then the fourth electron we have placed here. So how you will do the calculation? If it is in terms of dq, now it will be -4 into 3 and 6 into 1. That means -12 plus 6 is -6 dq. But if you are doing the calculation in terms of del O, it will be -0.6 dq. Okay. So why there is negative sign? Because it is lowering in energy. That is why there is a negative sign. This is not lowering in energy. There is positive sign. Though in the next slide you will see the calculation that we will do. There we will consider the opposite. So both things you should have proper idea, so that in some cases if in question it is given in terms of negative sign, then also you will be able to do the solve the question. Okay. So here we have taken this for T2G set we are considering minus sign and plus sign for EG set. But reverse may be the case, but that doesn't matter anything because numerical value will remain same. Only the negative sign that will change. So if there is negative sign, it will be positive. If there is positive sign, that will be negative. So I'm trying to say, suppose dq calculation if I'm doing in this way, that is 4 into 3. Now I am considering plus sign for the T2G and minus sign for EG. So now what will happen? 6 minus 12, sorry, 12 minus 6. That means now it is plus 6. So see, same value, only sign is different. Fine. So in the next slide we will see different possibilities. Distribution of d electrons in octahedral field. So in the previous example that I have just shown, D4 system. So what I have done, after placing 3 electrons in T2G, the fourth electron I have placed directly in the EG. But that may not be the case always. Sometimes it may be that instead of going towards EG, this fourth electron you are placing here. Now when you will do so? You will do so when this gap between EG and T2G is very high. That means the transfer of this electron to this high energy EG set, it is really difficult. Compared to that, if you are placing it here, though that is not according to Hund's rule, but it will be more energy saving. So that is the driving force, that instead of going towards EG, now they are remaining in T2G and making some pair. But here also another problem is there. When you are making this pair, basically what you are doing, you are placing 2 electrons simultaneously. So there will be some repulsion and you have to overcome that repulsion. And this is known as pairing energy. That means when you are placing 2 electrons together, you are making a pair, you have to overcome the repulsion energy, and that is known as pairing energy. So in both cases there is some problem. That is, when you are moving towards EG, then this del O value, if it is very high, that will be difficult. But if you are placing the fourth electron in T2G, then also you have to overcome pairing energy. So what to do? So basically what we do, you have to compare del O and pairing energy. If del O value is high, you will make pair. If pairing energy is higher than del O, then what you will do? You will shift the fourth electron in each. Okay. So it depends on which is overcoming what. That is, if del O is overcoming pairing energy or the reverse. Depending on that, distribution will be different. So that we will see now. So the filling of electrons in the d orbitals in the presence of ligand, it follows obviously Hund's rule. Now when it is d1 configuration, d2 configuration on d3, there is no such problem because you just place the 3 electrons or 2 electrons or 1 electron in T2G. But the problem arises when the electrons, that is the 4th electron, is now coming into the picture. So in case of d4, there are 2 possibilities. 4th electron, it may go to higher energy Eg, or it may make the pair in one of the T2G electron. So in this case, what we'll do, preferred configuration will be that one which is having lower energy. So look at these 2 possibilities. The first possibility, we are placing the 4th electron in Eg, and the second possibility, we are placing the 4th electron in T2G, not Eg, and this is known as low spin, this is known as high spin. So probably you have heard high spin, low spin complex. So this is the meaning. And how we will choose whether this one, suppose this is number 1 condition, this is number 2. So whether 1 will happen or 2 will happen, how to know that? It depends on del O and pairing energy. So P is basically pairing energy. Definition of pairing energy, look at the definition. It is the energy required to pair 2 electrons overcoming the electron-electron repulsion in the same orbital of a metal. So if this pairing energy, if it is lesser than del O, that means del O is greater than P. So what will happen? Now the electron will prefer to remain in the T2G because this gap is very high. Though in the picture it seems as if in both picture this energy gap is same, but actually in the second picture it is high. Okay, just assume it. So it becomes more energetically favorable for the 4th electron to occupy T2G orbital, and ultimately the configuration will be like this: T2G4 Eg0, right? But if it is that del O is lesser than P, now the 4th electron, it will prefer to remain in one of the degenerate higher energy Eg orbital, and now the configuration will change to T2G3 Eg1. So now if you do the calculation for CFSE, obviously the value will be different, right? Because in this case, what you will do, you will multiply 3 with minus 0.4 and 1 into minus plus 0.6. But in this case, what you will do, it will be 4 into minus 0.4. So these 2 values are not same. Okay. And remember, when you are doing this type of forceful pairing, because it is not natural pairing, it is forceful pairing, then only when you are calculating a CFSE, you have to consider pairing energy. So suppose if you are doing the calculation for T2G4 Eg0, what you will do, 4 into minus 0.4. So it is minus 1.6. Okay. But you also have to consider plus P. That means as you have made this forceful pairing, so you have to consider this energy also. But sometimes there may be natural pairing. Suppose if it is D8 configuration. So for D8 configuration, suppose you are placing first 3 electron, then 2 electron, 5 done, then 3 more electron. So here the pairing that you are doing, it is not forceful, it is natural. You have to do it. So in this case, you don't have to consider P. So sometimes in question, if it is asked calculate CFSE, just be careful whether it is forceful pairing or natural pairing. If it is natural pairing, you don't have to consider P value. Fine. Any doubt? Is it clear when you have to choose the first type of distribution or the second type of distribution under 2 different situations? And that depends on whether del O is high or del P is high. Okay. So now we will see different CFSE value. So this is a general expression, T2GX EGY. It may be X and Y may be any value. Suppose T2G3 EG1, T2G6 EG0, it may be anything. So for X number of electrons, here we have multiplied 0.6. See here negative sign is taken for this one. So what will happen? it will remain same. Numerical value will remain same, negative sign will be changed. So it doesn't matter anything, fine. And pairing energy, here this capital P is basically pairing energy and small p is how many number of pair you are actually making. So small p, total number of electron pairs compared to corresponding high spin configuration. That is compared to high spin, how many forceful pairing you are actually doing. And capital P is mean pairing energy. So for all the x, you have to multiply with 0.4 and for y 0.6. Negative sign, it may change in different places. You will see different types of calculations are done. Now in this table, we have configuration D4 to D7 because only for D4, D5, D6, D7, two situation may arise. High spin situation, low spin situation. But if it is D1, D2, D3, obviously there is no choice. There is only one possibility. Similarly, if it is D8, D9, then you do not have any two possibilities. You have only one possibility. So that is why in this table we are focusing only on these four configurations. So if it is high spin, suppose D4, D4 if it is high spin and this is low spin, so two possibilities are there. So when it is high spin, the del O value is not so high, and here we will place the electron like this, but if it is low spin, it will be like this. Now the calculation is also different when it is high spin and when it is low spin, fine. So CFSE value when it is high spin, it will be 3 electron in T2G, so this is basically T2G 3, EG1, okay. And for low spin, it is T2G 4, EG0. So it is T2G4, you will multiply 4 into 0.4. And for pairing energy, as we are using the opposite sign concept, so there is a negative sign. So only one P you have to add. So see, this is the low spin calculation. And for this one, it will be 3 into 0.4 minus 0.6 into 1. That means 12, 1.2 minus 0.6, it is 0.6. But if you are following the opposite sign convention, that is also fine. In that case, there will be a negative sign before this and also negative sign before it. Okay. So this is for D4. You can also do the same for these other three. So practice it for D5, D6, D7. But as I have said that it is applicable only up to D7. Now suppose you have D9 or D8, then two situation you will see it will not arise. And why it is so? So suppose this is high, this is low. 5, 4 more. So what configuration you are getting? T2G6, EG3. But when you are considering low spin, actually both will be same. Now you are having no extra space. You have to move here. 3 electron. So see, this is also T2G6, EG3. Right? So both are same. There is no such individual H or L. Both are same. So that is why this table you can see it is only for D4 to D7, because before D4, D1 to D3 there is no only one possibility, and after D7 also there is only one possibility. Okay. So the calculation of high spin and low spin complex. Is there any doubt? Should I repeat? Now very important part is, what are the factors that affects the magnitude of del O? That is the gap between EG and T2G. So del O, when it is very high, that means the gap between EG and T2G is very high. And if it is low, the gap is also low. But what are the factors based on which you will be able to understand that yes, in this case del O will be high? So some factors are there. One by one we will discuss. The first important factor here we have is spectrochemical series, and this is totally about ligand. It has nothing to do with metal. It is completely based on nature of ligand. So some ligands are able to produce strong field, and as a result what will happen? The splitting will be large enough. But there are some ligands that will produce weak field, where the interaction between metal and ligand that is very weak. And when it is strong field ligand, the interaction between metal and ligand that is highly intense. So now when it is weak field ligand, there will be small splitting. That means del O is low. Now depending on these different types of ligands, it can be arranged according to their order of increasing field strength. So here the series that you are seeing in the left hand side, basically it is the weak field side, and the right hand side it is the strong field side. Mostly this convention is used. So as you are moving towards left to right, you are basically moving from weak field ligand to strong field ligand. Now one question may arise, when I will reach in the middle region, what will happen? So actually what happens when you are in the middle zone, both possibilities you can see. But another important thing that you will be just after this slide you will see that it is not just this del O value, it is not just dependent on the ligand nature, it is also dependent on the metal nature. So many factors together it plays role, and it decides the ultimate value of del O. Okay, so this is just one of the factors. It is not the sole factor, right? But mostly the common ligands that you will see is halide ligands that are very common and that are on the weak field side. So basically when you have any halide, Br minus, I minus, F minus, it is weak field. Water is up to water also, it is mostly considered weak field. But as you are moving after that, especially for EN, that is ethylene diamine, cyano, carbonyl, all these always form strong field. They are always behaving as strong field ligand. That means you can expect that here low spin complex will be favored. Remember low spin complex where we consider pairing, because in low spin complex what happens? Just look at the green box. It is actually low spin because the del O value is very high, so that is why you are bound to do pairing. So this case will arise, that is the left hand side, the green box, whatever information is there, that will arise only when you have strong field ligand. That is, you have cyano ligand, carbon monoxide ligand, any amine type of ligand. Fine. And the purple box, that situation will arise when you will have weak field ligand. But again, I am saying this del O, it is not dependent only on the nature of ligand. Metal nature is also important, but we will come to that point later. So this series is known as spectrochemical series. It is actually experimentally determined series. There is no hard and fast rule that based on which you can remember that which ligand will be weak field, which ligand will be strong field. You just have to remember it. There is no other way, right? Now all these are experimentally determined based on the absorption of light by complex compound with various ligands. So suppose keeping all the other factors same, you have just changed the ligand. Suppose I have taken any metal cobalt and now it is associated with 6 water. There is 3+ charge. That means oxidation state 3+, and cobalt is the metal. Now keeping the metal nature same, that is again I have taken CO, but now I have changed the ligand to some other strong field ligand. So suppose if it is cyano, oxidation state is still +3, but cyano is anionic ligand, so now outside there will be 3 negative charge. So see what I have done, I have kept the other factors constant, because if you change the metal obviously there will be effect. So there, when there are 3 to 4 variables, what you have to do, you have to keep the other variables constant so that you can compare only one variable. So that is why we have kept metal same, oxidation state same. Under that condition, we have changed only the ligand. So in this case, you will always see that for the first complex and the second complex, obviously del O for the first complex, it will be lesser than the del O of the second, because here cyanoligand is present. Okay, so this is the example. Some more example you can see here. Chromium complex we have taken. Now in all these cases, chromium is having +3 oxidation state. And metal same, oxidation state same, only ligand different. Now look at the del value. All these are basically experimentally determined values, and unit is centimeter inverse. Okay, so it is nu bar basically. Remember, 1 by lambda. Lambda having unit of length, but 1 by lambda, that will be centimeter inverse, which is also denoted by nu bar. So this is not you, though we are saying that del O is energy, but sometimes units are not directly the unit of energy. It may be unit of lambda inverse or nu bar, because nu bar is directly proportional to energy. So when this unit you have and we are saying that del O is increasing, basically energy is also increasing, because these two are proportional. So see, as we are moving from Cl to H2O to ammonia and at last cyan. Now look at the spectrochemical series. Cl, water, ammonia, Cl. That means as you are moving towards the other, that is moving down the other complexes, the strong field ligand nature is becoming more, that is the strong strength is increasing, right? So this will be the order of strength. Cyano is maximum. So that is why here, if we look at the value, this is maximum 26,000, then 280. This is 21,680, 70,000, 30,000. So the values are highly different, right? And all these values are experimentally determined. How? By the absorption of light by the complex compound. So different compounds are taken and experiment done, and these are the corresponding del O values, from which it is clear if you keep metal same, oxidation state same, and you are just changing only the ligand. So depending on the nature of ligand, del O value will change. Any doubt? Should I repeat? This is the first factor. Now, under this factor, some more discussion we will see here. So this complex, that is the first complex that you are seeing here in the purple box, it is actually iron aquo complex. Here oxidation state of iron is 3, because water is neutral. So whatever charge is present outside coordination sphere 3+, that will be the oxidation state. Now iron, when neutral, it has configuration 3d6 4s2. That means when it has lost 3 electron plus 3 oxidation state, configuration will be d5. So d5, all these electrons are placed in this way. Number of paired electrons 0. So this is basically E iso. Iso means isotropic field. Suppose if there is a homogeneous negative charge field surrounding metal, then all these d orbitals, they will be degenerate, and it will be this type of configuration. But actually that doesn't happen. So two situations we will see, because when it is d5 system, you can have two possibilities, high spin and low spin. So when it is high spin, look at the left hand side, it is T2G3 Eg2, and when it is low spin, it will be T2G5 Eg0. Now the calculation will also be different. See, 3 into minus 0.4, 2 into 0.6, and there is no pairing you have done because it is high spin. So CFS is 0. But when it is low spin, now 5 into minus 0.4, So here you do not have any Eg electrons. It is 0 into 0.6. And you have done 2 pairing forcefully. Remember, if it is D5, this is T2G. So the 4th electron, 5th electron, you are making 2 pair. So that is why 2 into P. Now putting the value of del O, which is 14,000, and P value 13,000 in centimeter inverse unit. So CFSE value, what you are getting plus 32,000 centimeter inverse. So this is a high positive CFSE value, which indicates that low spin complex is not favorable. But here you have 0 value. So this is favorable. So though we have shown both of these, it is our purpose is just to compare the two situations. So after comparing, what we have found that CFSE, that is stabilization energy, more, that is when it is very low, you have to consider that situation. So when it is water ligand, basically high spin complex is favored, right? So this is the complex, this is high spin, or sometimes it is also called spin free. Electronic configuration, it will be like this. This is accepted, not this one. And number of unpaired electron 5. So this is paramagnetic. And magnetic moment also you can find out using the spin only formula, n into n plus 2. So this is 5.916. So higher is the number of unpaired electron, the magnetic moment value will also be high. Now the next example we will see, we have now replaced H2O with cyan, keeping all the other factors same. Here also it is plus 3. So metal same, oxidation state same. Now again it is D5. If it is ideal situation, E iso it is 0, that is just same as you have seen in the previous case. But first we will see what is high spin case, and then we will see low spin. So when it is high spin, it is just like same, and here it is T2G5E. But this del O value, now it will not be same, because now the ligand is changed, the gap between EG-T2G is also different. Look at the del O value. Here it is 14,000, but now it is 35,000. So highly different, because you have changed the ligand. Pairing energy same, because pairing energy is dependent only on the electron. It has nothing to do with ligand. So it is same. And in the high spin, it is same calculation as you are seeing here. But now ultimately if you see, this is 0, but this is highly negative. And negative CFSE value indicates low spin complex is favored, because as I have said, lowering energy is always favored. So here lowering energy is favored compared to 0 situation. And you will call this complex low spin or spin paired. Magnetic property C, now you have only one unpaired electron. Why? Because it is 2 pair and 1 unpaired electron in T2G. So that is why now the mu spin value, spin only value 1.732. So from Bohr magneton unit, that is a value that we have found for in Bohr magneton unit for magnetic moment, that clearly suggests that higher is the number of unpaired electron, higher will be the magnetic moment. So paramagnetism is very high here, that is in case of water complex, but paramagnetism nature is less in case of sand. So the difference between these two, is it clear? And how to choose between high spin and low spin? So when it is water ligand, weak field ligand, high spin complex favored, which is clear from the calculation. When it is cyano, that is strong field ligand, then from both calculation it is clear that low spin is favored. Okay? Any doubt? Now the second factor on which del O value is dependent, now it is related to metal, and it is metal's oxidation state. Remember, a higher oxidation state always leads to larger splitting. Now see, we have kept metal same, ligand same, and both are octahedral. Obviously we are discussing about octahedral, it has nothing to do with tetrahedral, fine. Only oxidation state is different. 3 plus, 2 plus. Okay. So keeping other factors same when you are changing only the oxidation state of metal, higher oxidation state means the transition metal is now more electropositive, more electron deficient, and ligands are approaching towards metal. Now the interaction between metal and ligand, as metal is very electron deficient, now the interaction will be high. So when the transition metal is more electropositive, the interaction between the negative donor part of the ligand and the metal will increase, and this increases the orbital overlap. As a result, what will happen? There will be lowering of energy of bonding interaction. That is, we know whenever there is lowering in energy in bonding, equal amount of increase in energy also happens in antibonding. So as a result, what will happen? The gap between these two, that will highly increase. So the final conclusion is that when you have very high oxidation state and low oxidation state, obviously in case of high oxidation state, Delo value will be high. So that is why there is a greater than sign here. Some more examples also we will see. Look at these two. Iron, iron. Water, water. Only difference oxidation state. And look at the Delo value. It is so different. Similarly, second example. Metal same. Ligand same. Oxidation state different. Now look at the difference. Fine. One more example we will see. Ruthenium water complex. Same metal, same ligand, oxidation state different. So when oxidation state is 3 plus, now the value is very high compared to the 2 plus state. Okay. So is this factor clear? Now this factor is completely related to metals oxidation state. It has nothing to do with ligand. So that is why we have kept the other factors same. And this is second factor. The third factor that we are going to see, that is also related to metal, but what is that? That is actually from which series the metal that we are having in the coordination complex, that is from which series, because we know there is first transition series, second transition series, third transition series, right? So the second part, second factor, is it clear? Come to the third point, nature of metal atom. That means from which series you are having this metal. So just take very simple example. Suppose you have iron, just below iron ruthenium, and below ruthenium osmium. Okay, that means they are in the same group. This is 3D, this is second transition series 4D, this is 5D. So when you are keeping all the factors same, that is you are keeping oxidation state same, ligand same, you are just changing the metal. That is you are moving down the group. So what will happen as we are moving down the group, Delo value will increase. Now what is the reason behind that? The value of CFSE also determined by the transition series to which the metal belongs. And the order for this is like this. That means if it is from 5D, it will have maximum Delo value. But remember, you have to keep the metals when you are comparing in the same group. If you are changing the group, then comparison will not be correct, right? So the metals that are from 4D and 5D series, that is ruthenium and osmium, compared to Fe, they will have more tendency to form low spin complex, because now the Delo value is very high. Now the reason is, as you are moving from 3D to 4D to 5D, the size of the d orbital is increasing compared with 3D, because 3D is more compact compared to 4D and 5D, more tight. And as a result, as their size is very large, interaction with the ligand orbitals is also very high. As a result, Delo value will also increase. Okay. So here we have example, cobalt, rhodium, iridium, all are from same group. But cobalt is first transition series, rhodium second, iridium third. Oxidation state same, ligand same, ammonia. Look at the Delo value. It is increasing as we are moving down the group. So in this graph, we have taken Delo value in centimeter inverse unit in the y-axis, and in the x-axis we have group 9 metals. So this is for cobalt. This value is from rhodium. This is for iridium. All are in +3 oxidation state. So see, the values are highly different as you are moving down the group, right? So this is nature of metal atom or ion, because metal atom means when it is 0 oxidation state, ion means when it is N+ state. So under metal you have two factors that you have seen. One is oxidation state of metal, another one is from which series that is the metal belongs to. Fine. Now if we combine these two factors, that is factor 2 and 3, if you combine both of these, you can get a new type of order, which you can see here. Some metals we have from 3D, then we have molybdenum, some we have from 5D and 4D. Now see, if you look at Fe3 plus and ruthenium 3 plus. Now Fe and ruthenium, they are from same group. So see how different it is. Ruthenium 3 plus is far from Fe2 plus, and this is increasing del O. Fine. Similarly, palladium and platinum, they are from same group. Nickel, then palladium, then platinum. Now look at these two. Pt is from 5D, Pd is from 4D. So as it is from third transition series, it is having higher value of del O compared to Pd4 plus. Okay. Then we have rhodium 3 plus, iridium 3 plus. So obviously iridium is just below RH, that is rhodium, it will have higher. And within same series, that is MnNiCO and oxidation state 2 plus. So there is also change. So that is actually completely different thing. That depends on when you are moving along the series in a particular period. If you consider, that is just consider the first transition series, you are moving from scandium, titanium, chromium from left to right, keeping the oxidation state same. Then also there is some variation, but that we'll see separately. Right now just we have combined these two factors, and this type of series you can find. So today we will end here regarding all the slides. Is there any doubt? Next day we'll see crystal field splitting in tetrahedral field, because if you keep all the factors same, that is metal same, ligand same, oxidation state same, every three, that is all the 3 points that we have discussed, all the 3 points are same. But now from octahedral you are switching to tetrahedral. Then also there is some variation that you will see in the next class. So today we are ending here. Thank you for listening.